Welcome to The Explainer. Today, we're shattering the illusion that building a fancy machine learning algorithm is the finish line. We're actually going way beyond the model itself to explore the massive, living ecosystem required to keep these systems alive in the real world. So if you think the neural network is the whole story, you're definitely in for a surprise. Let's break down exactly what it takes to launch, maintain, and monitor these incredible tools.
Okay, let's dive right in with a pretty wild statistic. The actual ML model code, that incredibly complex math you spend hours, days, or weeks perfecting, often represents just 5%, or sometimes even less, of a real-world production system's total codebase. It's literally just a tiny drop in a massive bucket of surrounding infrastructure.
Since the model is just a tiny piece of the puzzle, here is our blueprint for exploring the other 95% today. We'll cover 1. The ML ecosystem. 2. ML paradigms. 3. Transforming data. 4. Deployment testing. 5. Monitoring pipelines. And 6. Critical questions.
All right, Section 1, the ML ecosystem beyond just the model. You wouldn't believe the sheer amount of resources that have to be devoted purely to wrangling input data and maintaining the infrastructure around it. Think about it. You have to build bulletproof pipelines for collecting raw data, verifying its quality against super strict schemas, extracting engineered features, and then actually spinning up the servers to serve predictions to your users. And honestly, that's all before we even touch on the continuous monitoring part.
Moving right along to Section 2, ML paradigms, and choosing your architectural path. Building a system means making some pretty fundamental architectural choices right out of the gate. You basically have a fork in the road. Static training, which is offline, cheaper, and simpler, but risks going stale. Or dynamic training, which constantly adapts to new data online. Imagine you have a model predicting flower sales. If you statically train it only on summer data, it's going to perform terribly when Valentine's Day rolls around. Dynamic training solves that staleness for sure, but it demands way more monitoring to ensure it isn't ingesting corrupted data on the fly.
And, we see that exact same trade-off when it comes to inference. Static inference is fantastic for the cost and speed of cached common items. Actually, if your model takes an hour to compute a prediction, static batching is pretty much your only option. But what if a user queries a totally unique, never-before-seen phrase on a search engine? For those rare long-tail inputs, you absolutely need dynamic inference to generate a prediction on demand, even though it's much more compute-intensive.
Section 3, transforming data, where timing is literally everything. After you pick your paradigms, you hit another major crossroad, deciding exactly when to transform your raw data into engineered features. Doing it before training is a great one-time process that saves time, but you risk creating a disconnect between your training and serving environments. On the flip side, transforming during training guarantees perfect consistency. The model ingests raw data directly using the exact same code you'll use in production. But this definitely adds complexity. For instance, if you normalize data batch by batch, a z-score of -2 might mean something completely different across varying batches.
Let's move to Section 4, deployment testing. Think of this as your essential pre-launch checklist.
Let's say you're building a fun little binary classification model, maybe one that predicts unicorn appearances. To confidently update that model, you absolutely must ensure reproducible training. By locking down randomness, like deterministically seeding a random number generator and initializing components in a fixed order, you create a safety net. That way, you know a jump in accuracy came from your genius engineering and not just a lucky random seed.
Now, before you even think about hitting that deploy button, you need to rigorously validate your serving infrastructure. You definitely don't want to retrain an entire massive model just to test a tiny API tweak. So running just a single step of gradient descent makes for a brilliant unit test. And always stage your new model in a sandbox server first. You've got to ensure it plays nicely with your dependencies before it goes live.
Section 5, monitoring pipelines. Once you're live, it's time to play detective.
Here's a sneaky truth about ML monitoring. A phenomenal overall metric can absolutely mask a terrible subset. This is why tracking real-world impact isn't enough. You must monitor specific data slices continuously. Your unicorn predictor might have 99% overall accuracy, but if it completely crashes when analyzing inputs specifically from the Sahara Desert, well, you've got a major blind spot that needs fixing. Let's dig into some of the hidden traps you'll be hunting for, starting with training serving skew. This is a big one because it violates the golden rule of machine learning. Training and production environments must mimic each other perfectly.
If the input data available during serving fundamentally differs from what you trained on, your model is basically flying blind. Take a second and really think about this scenario. If you're building a model to predict daily revenue for a store, why might using the number of customers as an input feature cause a massive skew? I mean, it sounds highly predictive, right? More customers, more revenue.
Well, it's a trap. You cannot use features during training that simply won't be available to the model at prediction time. If you train your model using the final end-of-day customer count, it'll look like an absolute genius in testing. But in the real world, at 9 a.m. when you're asking for a prediction, that daily customer count doesn't exist yet. Your model will crash and burn.
Another highly deceptive bug you've got to watch out for is label leakage. This creates artificially fantastic training metrics because the ground truth label, the exact answer you're trying to predict, inadvertently bleeds into the clues you're giving the model. It's like the model secretly has the answer key to the test. Picture this real-world hospital scenario. Your classification model gets incredible evaluation scores predicting cancer during testing. You used age, vitals, test results, and hospital name as features. But in practice, on fresh new patients, it fails completely. Can you spot the leaked feature? It's the hospital name. The model didn't actually learn to detect cancer, it just memorized which hospital names belong to specialized cancer treatment centers. It cheated. And worse, real, newly diagnosed patients haven't even been assigned a specialized hospital yet. So that feature won't exist when you actually need the prediction. Finally, Section 6, critical questions for maintaining your ecosystem. Once your system is up and running, you have to relentlessly question its health. If a specific feature only gives you a tiny fraction of a % of accuracy, but it constantly breaks because an upstream data source goes down, cut it. Ruthlessly trim unhelpful features to reduce your maintenance costs. And always, always monitor for numerical stability. You do not want your model weights suddenly returning not a number or infinity out of nowhere. And finally, beware the dreaded feedback loop. This is a dangerous cycle where a buggy model inadvertently manipulates the data used by another model, or even its own future training data. It's an interconnected ecosystem out there. If a buggy stock prediction model accidentally drives the stock price up, a completely different model might see that artificial increase and make a terrible trade based entirely on that first bug. I'm going to leave you with this final provocative thought to ponder about your own systems. Are your model's outputs secretly manipulating the very reality it's trying to predict? If your awesome traffic model tells everyone the beach will be packed and they all decide to stay home, the beach ends up totally empty. Your model was technically wrong, but only because its own prediction fundamentally changed human behavior. Keep asking the hard questions about your ecosystem, and we'll catch you next time on The Explainer.